All right, today we are diving into a theory that might just flip everything we think we know about the brain completely on its head. It's called the Brain Kinematics Model, and it basically says that this massive piece of the puzzle has been staring us in the face the whole time. But to even see it, we've got to start by questioning the one thing we all thought was a sure bet.
So, you've probably heard it a million times, right? The brain is just a super complex biological computer, a tangled mess of wires firing off electrical signals. But what if that whole metaphor is just, well, wrong, or at least fundamentally incomplete? What if the actual stuff the brain is made of, its physical squishiness, matters just as much as any signals zipping through it?
Okay, so before we get to the new groundbreaking idea, we've got to take a look at the current champ. For decades, neuroscience has really been dominated by one single powerful story about how the brain works. And that's the textbook story, right? The idea that the brain is this incredible electrochemical machine. It's all about neurons, synapses, and a soup of chemicals like dopamine and serotonin that are zipping around, making everything happen, from you lifting your finger to feeling happy or sad. And look, don't get me wrong, this model has been incredibly powerful. I mean, it's given us these amazing maps of where neurotransmitters hang out, like dopamine hubs, and it's the entire foundation for modern drugs like SSRIs. But it's got some pretty big blind spots. It doesn't have a good answer for the physical context, like how and why are these chemicals made and released right then? It really struggles with the mystery of self-regulation, and it kind of hits a wall when it comes to the big emergent properties, like consciousness.
And it all bubbles up to one massive question. If our brain is basically just a complex chemical clock, what in the world keeps it ticking perfectly on time for, say, 80 years? How does it stay so perfectly balanced for an entire lifetime? The standard model honestly doesn't have a great answer for that.
And that brings us to the missing piece of our puzzle. It's a physical clue, and it's something so obvious, so fundamental, that we've almost completely looked right past it. Think about it. Your brain isn't a hard drive. It's not a rigid circuit board sitting in your skull. It's soft. It's a physical, gelatinous medium. It literally jiggles and moves. And it turns out, this physical jiggliness isn't just some random detail. It's absolutely fundamental to how the whole system works. So the technical term for this stuff is viscoelastic tissue. The easiest way to think about it is like memory foam. It has some solid-like properties, right? It holds its general shape, but it also has fluid-like properties. It can squish, deform, and absorb pressure. And this physical property, this squishiness, that's our central missing clue. And that clue, the physical nature of the brain, is right at the heart of this new theory. It's called the Brain Kinematics Model, or BKM for short, and it puts the brain's physical body front and center in the story.
So, the BKM says brain activity isn't just one thing happening. It's actually three interacting layers. First, you have the one we all know, the fast, locally electrochemical signals. Then, you've got the electromagnetic fields that help synchronize bigger areas. But then, here's the game changer, the third layer, mechanical strain flows. We're talking about the actual physical pressures and tensions that ripple through the brain's soft tissue.
This creates this absolutely fascinating two-way street. When neurons fire, it creates a tiny bit of physical strain in the tissue around them, kind of like plucking a guitar string. But here's the cool part. That physical strain, the tension in that string, then feeds back and actually changes the neural activity itself. It's this constant physical electrical conversation happening inside our heads second by second. Okay, that's a cool idea. But so what? What does this new model actually do for us? Well, as it turns out, it offers some pretty elegant solutions to those old mysteries that the standard model just couldn't quite crack. Remember that big question about the 80-year clock? The BKM basically says, there is no clock. There's no preset schedule. Instead, self-regulation is an emergent property. The brain is just constantly, physically trying to find a state of equilibrium, a balance of all that strain across its tissue. And that physical balancing act is what naturally keeps all the chemical and electrical stuff in check. This model also completely reframes how we think about neurotransmitters. It suggests their release isn't just triggered by some chemical timer. No, it's triggered by the physical state of the brain tissue. So, for example, dopamine gets released when there are steep gradients of physical strain. Think about those moments of intense novelty or motivation. On the flip side, serotonin tends to flood the system during states of physical relaxation and low-frequency strain, like when you're calm or asleep. It's a whole new physical dimension to our brain chemistry. Now, this is really important. This isn't just some cool thought experiment. It's a real, testable scientific theory. The BKM makes concrete predictions that you can actually prove or disprove in a lab.
For example, the theory predicts that the physical stiffness of your brain tissue should directly correlate with the frequency of your brainwaves. You could literally measure both and see if they match up. It also predicts that something as simple as paced breathing, which physically changes the pressure inside your skull, should measurably alter your brain rhythms. These are real, doable experiments.
And, if this model gets confirmed, the implications are huge. Clinically, we could develop totally new biomarkers for things like cognitive decline based on tissue mechanics. In the applied sense, we could design non-invasive therapies, like targeted breathing exercises, to actually improve brain health. And theoretically, it points toward a unified model of the brain, one that finally connects its physical structure, its movement, and our thoughts into one cohesive story. So all this leaves us with a really fascinating question. For the last century, we've studied the brain as a chemical and electrical machine. An amazing one for sure. But what if the next great leap forward in understanding, and maybe even healing, our own minds lies in finally understanding them as physical, mechanical things?